Okay, how are you guys doing?
Good.
The homework work out appropriately for both of you now? Okay, good. Because
It
it's
says it's overdue, though. I think that the due dates need to be changed.
probably except for last year.
Yeah.
Nathan started on that on Monday, but he must not have gotten through because of classes. So yeah, we'll get that updated. We'll get it updated and turned in tonight. How's that?
Yeah.
Do you know how to turn it online, Chad?
Yeah.
Okay. All right. We are going to continue moving forward in learning basically how we do quantum mechanics. So the first lecture was talking about a little history of how it developed. And then last lecture, we talked about the statistics involved. And now we're going to start actually doing some things that are more quantum mechanic-y, but still not really doing quantum mechanics. So I have starting here two equations. What do we call this upper equation? The Schrodinger equation. I was going to say I'm not German. I actually am a quarter German, but I still don't feel comfortable pronouncing the O umlaut. It's something between Schrodinger and Schrodinger. It depends on who you talk to, which way they pronounce it, and I'm pretty sure it's in between. That is our wave equation. That's the equation that we use to get our wave functions. And we will be using this to get wave functions. For today's lecture, we are simply taking, okay, this is the equation that our wave function must fit into. And so we're going to use it to learn a few things about the wave function that comes from this wave equation. Now, the lower equation is the way we calculate an expectation value. Now, from last class period, you know the expectation value means that if you have a statistic, in fact, this is on the next slide. Let me just turn to it. It's not. If you have a statistically significant number of samples of an identically prepared system, and you make measurements of position, for instance, the average of that is the expectation value. And so what we learned from what we did last class period was to find the mean or the expectation value. We did the sum. Since I put X, I better put X here. The value of X for each measurement times the probability of getting that. We added them all up. Well, in quantum mechanics, we're usually dealing with a continuous thing, like position is between here and here, and we have continuously varying possible positions. And so in that case, a summation becomes an integral. And I'm going to put from A to B of X times the probability of being at position X dx. Now, before today's over, I'm going to write this a third way. But for now, that's what this equation is. This is over all possible space, so it's going from minus infinity to plus infinity. I did from A to B just because I was choosing to be a little contrary. We have the value of X times the probability. This psi dx is the probability of being in the region X dx. So my P of X psi mod squared is what I'm putting in there. Now, of course, it always seems just a little mealy math because I said P of X dx is the probability of being in region dx. And now I'm putting P of X is just the psi mod squared. Hopefully you can reconcile the two ways of speaking because it doesn't quite mesh. So let's get into the material. First, some rules about the wave function that we will learn the reasons for later. These I'm just giving them to you now, the first two, and later on we'll learn why they're that way. And we'll learn why there's the parenthesis at the end of the second line. So our wave function, psi, must be continuous over space. That is, you can't have 0 probability here and 50% probability here without having it change between. It can't just discontinuously jump. And furthermore, the slope the d psi dx also cannot discontinuously jump unless you have an infinite potential boundary. So in real life, infinite potential boundaries are unlikely. In textbook problems, well, our first problem will have a discontinuous or an infinite boundary because it makes our calculation easier. Now, the third one is one that makes complete sense, and yet it really needs to be said. So let's start with just a really simple question. If I have an electron that's somewhere in this room, and so I sit down and I calculate what the probability of the electron being in each little section of the room, what am I going to get if I add up all of the probabilities for the entire room? 1. That's what normalization means. It means that we have to have our wave function such that the probability of finding my particle in all space has to be 1. That makes sense, right? Now, mathematically, it's a little more involved. We call the name of this normalization. It's normalized if the sum of all probabilities comes to 1. And so to do that, since the probability is psi mod squared dx, then what we have to do is we have to sum it, integrate, over all space. And that has to equal 1. So that is what we call our normalization condition, the equation I wrote right there. Now, if you read, I don't know if you read the textbook or not, I do lecture pretty closely to this textbook. This is a complicated enough subject, I really think that you need to be able to read through the textbook and correlate the two very closely. And he says, but wait, how is it that we can go and impose a condition on the solution from the wave equation? The wave equation should give us everything. The wave equation is known as the Schrodinger equation. And so the first thing is, if you look at that Schrodinger equation, our wave equation, you see that it has psi in every term. So that means if psi is multiplied by a constant, that constant is just multiplied through every term, and the equation is still going to be true. So the solution to the wave equation always is going to have the ability to be multiplied by a constant, and it's still a solution. That's actually an important rule. If you have a solution to this that is non-normalizable for any reason, that is, you can't multiply by constant, it stays the same, and you can't do that integral, we call it square integral, or integrable. If you can't normalize, if the integral is, for instance, infinite, or if the integral is 0, then it's not a valid solution to this equation. It may be a mathematical solution, but not a valid one, not a quantum physics one. So all of our solutions to this have to be normalizable. It can't be, obviously, psi equals 0 is a solution to this equation, because 0 is equal to the second derivative of 0 plus 0. But that is not a valid solution. It's what we call the trivial solution in our calculus class. It's a solution, but it's not a valid one. Now, if you look at pages 13 to 14, he goes through and talks about once you normalize it, it's going to always stay normalized. And it's an important derivation. I've got my textbook here so I don't mess up. I want to go through the derivation, adding in the pieces that are not there. As with any good textbook, I presume, he went through and he did the derivation, leaving some steps that he can put in his homework questions, fill in from here to here. And so I want to go through this to show that if we have a normalized solution, it will stay normalized. So we start by saying if it's a normalized solution, so So we have this question essentially. If psi of x and t is a normalized solution to the Schrodinger equation, then how does the normalization change in time? So that's written in words. The mathematical equation is what is d dt of my normalization condition, which is integral from minus infinity to infinity, or my normalization equation, psi star psi dx. That's basically the starting point. And I've already asserted, because normalization psi star integral psi star psi dx should be 1, if it's going to stay normalized, then this derivative should be 0. If this derivative is not 0, then it's not going to stay normalized, right? Because it'll be drifting in time. Okay, so we have if psi of x and t is a normalized solution to the Schrodinger equation, then how does the normalization change in time? So my equation here is, what is the time derivative of my normalization equation? Right, this thing in here is the calculation you do. You set this equal to 1 to normalize. And so if this is equal to 1, that should be, the derivative should be 0. But if it's equal to 1 at time equals 0 and it's not equal to 1 at some later time, then this is going to be a function that varies. So, and I've already said the answer is this had better come out to be 0. That is, once normalized, always normalized. But we're checking that. We're not just taking it for granted. And you know, the author says this is really important because it would be useless to try to do quantum mechanics if you have to renormalize every second. But the real reason this derivation is here is not that important principle. It's to get us a little familiar with the kinds of manipulations we do with the Schrodinger equation. So that's the real reason for this derivation. So let's get started. The first step is I have a time derivative of an integral with respect to x. Now remember, psi is a function of x and time, position and time. But if I'm doing that integral dx, what is the integral of psi mod squared a function of? If we integrate over x, then the x is going to disappear, right? Because we put in the limits on the x, and it's only a function of time now. So that derivative d dt, I can bring inside the integral sign, but I'm going to have to change it to a partial because inside the derivative we have x's, or inside the integral we have x's and t's. But that's only a derivative with respect to time, and the function is not going to have any x out here. That's why I didn't have to be partial. But when I put it in, it's going to be equal to a partial derivative. Now, this is a time when I had better ask, are you comfortable with me writing a partial derivative? That's something you're comfortable with. It's not, oh, I'm not sure what to do with it. Okay. Just to reiterate what it is then, you say for the most part, so you probably understand what I'm saying here, but just to make sure. A partial derivative says everything's not my variable, differentiation is a constant. So, oops, I put an x. That should have been a t, right? We can't magically change. Magic is prohibited. So this here is with respect to time. So any time that is in this function, I'm just treating it as a constant in terms of my derivative. Any time. Anything that's not time is a constant. Any x's in here are just treated as constant. So it's easier to do a partial derivative than a full derivative for that reason. Well, now that we have this, let's expand what d dt of psi star psi is. I take that derivative, what rule do I use to take the derivative of psi star psi? Product rule, right. We're not going hardcore here.
Just making certain.
Yeah.
Psi star is, I don't know if it's a different thing.
It's an independent variable or independent function compared to psi. Okay. So that's going to be psi star d dt psi plus d psi star dt. I should put this up here so it's more clear. So I just did the product rule there. And now we turn to the Schrodinger equation. I'm going to go back a few slides to the Schrodinger equation. And notice we have right here, we have partial derivative of psi with respect to time. Now, for simplicity's sake in this derivation, we're saying let's take the case where the potential function v is 0. Right, that doesn't have to be the case. Actually, I said for simplicity's case, if you look at the textbook, okay, so if you look at equation 1.23 and 1.24, he didn't put v as 0. So I guess I'll do it the way he did. It's just easier to not have to worry about it, but it does come out. So I'm going to take this equation right here, which now looks super busy with all the stuff I've drawn on it. And I'm going to solve it for d psi dt. That is the partial derivative of psi with respect to time. Notice I'm going to have to divide both sides by IH bar. And so I have, from the Schrodinger equation, the partial of psi with respect to time is equal to over IH bar so, and of course, I mean, I should know the Schrodinger equation by heart, but I'm just making sure, yes, got the minus sign there. So there is what d psi dt is. Or to combine, instead of having the big ugly over IH bar. And yes, that's a psi, not a 4. If I made it come up higher, it'd be more obvious. You know what we don't like to do? We don't like to put over I. We can, and we'll, if we get that far in today's lecture, we'll see that when we put the momentum operator, sometimes we do. But it's more comfortable generally to replace a 1 over I with a minus I. Since I squared is minus 1, if I multiply top and bottom by I, I'll have I over I squared, which is minus I. Okay, so that should be the same as equation 1.23. I'm checking because you know I do make mistakes. But yes, that is the same as equation 1.23. Now, how do we go from equation 1.23 to equation 1.24?
We just use the product rule. It's the same thing.
Not the product rule. We just take the complex conjugate of every term. Right, because the stars means complex conjugate. And so d psi star, because that's the complex conjugate, dt, equals I becomes minus I, h bar over 2m, d second psi star dx squared plus, because the minus I became a plus, IV over h bar psi. You may have, oops, I forgot the star. You may have some quibbles that we need to deal with. Number one is, why is there no star on the t or the x? Okay, the answer is because time and position are not imaginary. You can't have an imaginary time or imaginary position. So there is no need to put a star there because it's the same thing. Likewise, there is no imaginary mass, and the constant h is all real. So these terms that are all real don't need to have a star. Why is there a star on this as well as changing the sign here? Everything that has an I needs to have its sign changed. So we have I times a function, we change the sign on the I, and if there's another I in the function, we need to change the sign everywhere there's an I in the function. So we have to do it to both. And now the final thing, why is there no star in the V? Right, we must have a real potential energy function. Not imaginary, or not a complex. If it has an imaginary part, it's complex. Okay, so now we have those two things, and we can look back at our equation. We had d dt of psi star psi was psi star d psi dt plus d psi star dt psi. So I'm just going to multiply through then to get so there's the first one, and then I'm going to have, notice it was a plus sign, plus, then the derivative with the psi star is minus. So there is my partial derivative with respect to time of psi star psi. But I can simplify this now because we see this term here and this term here. Keep in mind there's a psi star there multiplied through. Those are going to be on the top minus IV over h bar psi star psi. And on the bottom, plus IV over h bar psi star psi. So those two things are the same magnitude but opposite sign. They subtract out, which is why I was going to drop the V to begin with. But you can see that they disappear, provided that V is real. If V was not real, if V was complex, they wouldn't. So we're left with, oh, I forgot to put over 2m here. My mistake. As you may have noticed in my other class, if I make a mistake, I try to put it in a different color. That way it's clear when you come back. Yeah, there's where the mistake was. So I'd have IH bar over 2m times psi star d second psi dx squared minus d second psi star dx squared psi. Now we're going to go one step further on this. This is the second derivative, right? We are going to rearrange by recognizing that, and if you look at the textbook, it gives you the basis of what we're going to do here. If you recognize that psi star if you take that derivative, you're going to have to do the product rule 2 different times, and you're going to have that's what you get when you expand it. But if you look and see, you have this term here and this term here subtract out. And what's left, this here, is that there. So we can replace the term in the green box with the derivative. And so that actually is the last part of the equation, 1.25, the bottom of page 13. So the top of the next page, I'm going to write that. We now have found that d dt of psi mod squared is equal to I h bar over 2m d dx of psi star d psi dx minus and hopefully I have the signs right. Yes. So that's what we have determined so far. We have used the Schrodinger equation to get to this point. Without the Schrodinger equation, we can't get here. So this is only going to work if it's a solution to the Schrodinger equation. But now that we have that, we can go back to what we started with. We had the change in the expectation value, the d dt, that is equal to integral from minus infinity to minus plus infinity of what we just had. So d dt, or no, d dx. I'm going to put the IH bar over 2m outside. There's no point of the integral since they're constant. Now, life just got easier. Do you recognize why life got easier? Nope. I didn't either the first time I looked at this. We have the integral of a derivative. Do you remember the fundamental theorem of calculus?
Integral of the derivative just leaves you with the function.
Right. The integral of the derivative just leaves you with the function. So this is equal to I h bar over 2m psi star d psi dx minus d psi star dx psi. There's my answer, except for one thing. We had limits on our integrals. That's evaluated minus infinity and plus infinity. And at this point, you have to think back about our rules for the Schrodinger equation. The solutions to the Schrodinger equation, these wave functions, must be square integral. That is, they must be normalizable. To be normalizable, that means if you integrate over all space, it can't blow up. Right? It has to go, if it doesn't blow up, your functions have to approach zero as you approach plus and minus infinity. That's the only way that you can make it integrable. So going along with that must be normalizable is the absolute requirement that psi and psi star have to approach zero as x approaches infinity. And if they approach zero as x approaches infinity, that means their derivatives are also going to approach zero. So each of those terms there, psi star times the derivative of d psi dx, has to be zero at infinity. And so this whole thing must equal zero for it to be a normalized function. So now in the end, we had two things. It has to obey the Schrodinger equation, and it has to be something that can be normalized. But we started by saying if it's normalized, what's going to happen to the normalization? So it had to be normalizable, or else we could have started. All of this outcome, like I said, it's an important outcome that says that once normalized, always normalized. But the work that we did, the reason for this problem was so we could see how we can manipulate and use that Schrodinger equation for more than just to find the wave function. Now that took a lot of time. I only have 18 minutes left. But it's a valuable point. Any questions before I move on from here? No? All right. Now the expectation value, we've talked about what it means and how we write it. So this here is redundant. It's a reminder from last class period. The expectation value for position is written less than x greater than to give us the expectation value for position. Now how we do this is using operators. So operators are mathematical functions that operate on another function. And the simplest operator is just a constant value. 5 is an operator. If I have 5 acting on the function x squared, I get 5x squared. It's pretty simple. But pretty much anything can be an operator. A derivative can be an operator. A derivative can act on a function that gives you a new function. So operators are functions that act on other functions. In quantum physics, we limit ourselves to very specific rules on our operators. And the one rule I'm going to talk about now is that the operator acting on the wave function needs to give me a value times the same original wave function. So that is, if I have my x operator acting on psi, that needs to give me the x value multiplied by psi. If I have the momentum operator acting on psi, that better give me my momentum value times psi. So I'm going to try to use the nomenclature, putting a subscript OP anytime I'm using an operator. Our textbook does not. Some textbooks will use a little array like we use for a unit vector to indicate an operator. Others will use the subscript OP, and ours doesn't do either. So with that, then we can say that if x operator psi is equal to x times psi, then if I put psi star in front, I should have that. But now that I've done the operation and I have the actual value, that's just going to be equals x psi star psi. Now you're not going to see this lower line anywhere because we are, at least for now, only going to write psi as a function of x. And if we write psi as a function of x, then the p operator actually doesn't operate on that function. You don't have it the way you would like. You can write psi as a function of momentum and time using a different version of the wave equation, and then the lower one works and not the upper one. So this one here is the one we're going to be using right now. But you notice that psi star x operator psi is equal to x times psi star psi, which is what we needed to find the expectation value. Go back to the first slide here. To find the expectation value, we need x times psi mod squared. But x times psi mod squared is psi star x psi. The order is important. You can't put psi x psi star. It needs to be psi star x psi. Because if you put psi x psi star, then you'll get x star. It actually, I mean, x is real.
Yeah.
So it doesn't, in that case, it wouldn't matter. But for instance, when we use other operators, it makes a difference. So the order needs to be preserved. Right. There, you can find cases where it won't harm you, but in most cases it will. So with that in mind, we're now going to actually go ahead and find normalization and expectation values for a problem. This is problem, I think, chapter 5 from the chapter. It doesn't have a solution there because it's actually there to be a homework problem. And so I want you to kind of tell me what to do at this point. How do I normalize this function?
Set it to 0 and take the derivative from, or take the integral.
Okay, integral, but not set equal to 0.
But it should equal 0.
It should equal, what you're looking at is the derivation on what happens to the time variation. But normalization is the sum of the probabilities over all space must be 1.
So take the integral from negative infinity to infinity equal 1.
And what is my integrand? Well, it's psi star psi, right? So it's going to be, I'll first write psi star psi dx, and then I'll fill in what that is, which is what you were starting to say. So that's going to be a star. Nobody said our normalization constant had to be real. It can be complex. E to the minus lambda absolute value x, e to the minus I omega t. Notice I changed the sign on the I there for the complex conjugate.
So the A is the first psi star.
Yeah.
And then the rest, the 2E, the rest of that is the second psi.
No. This whole thing here is psi star. The whole black is psi star. And then the red is going to be psi. So there I've substituted in psi and psi star. Before I go any further, let's go back and check things I said. Things that psi must do to behave. Obviously, this problem has a behaving psi, one that is valid. But the things it had to be were it had to be continuous. is this function going to be continuous from minus infinity to plus infinity? Yes, because at x equals 0, you're changing from a plus x to a minus, or from a plus to a minus there in the middle, but it's going to be minus 0 at x equals 0 in both cases. So it's continuous over all space. Is the derivative of this going to be continuous?
I didn't know what it is, but I don't know.
Actually, it's not.
Or it's not. Well, how do
How do I know that? Because at x equals 0, if I take the derivative of this, the derivative of this function is times plus or minus lambda, because you have to bring down the derivative of the exponent, and because the absolute value, it's going to change the sign. And so the slope is going to have a discontinuous jump at x equals 0. Right? At x equals 0, it's going to be a is the slope. Or excuse me, a lambda to a minus lambda. So that means that this only corresponds if I have a discontinuous barrier at x equals 0. In fact, this is, I believe, the solution if you have a delta function at x equals 0. We'll learn about those later. So those are our things to check here. Now, taking this, a star is a constant, a is a constant, so I can rewrite this as a mod squared, integral from minus infinity to infinity. Now, e to the minus lambda absolute value x, e to the minus lambda absolute value x. Those are the same thing, so I just add the exponents. And then e to the I omega t times e to the minus I omega t. Add those exponents, what do you get? You get e to the 0, which is 1. So this times this just gives me 1. Who knows what to do to get this integral?
bring 2 down.
I actually have to do that. That's derivative, but I have to do something else first before I can do the integral. This function, right? This is psi mod squared, a mod squared times this. At x equals 0, if x is less than 0, then the absolute value of x is equal to minus x. If x is greater than 0, the absolute value of x is equal to x. Yeah. And so the function actually switches at x equals 0. So I need to break this into 2 integrals. I need to break it into integral from minus infinity to 0 of e to the 2 lambda x plus integral from 0 to infinity of e to the minus 2 lambda x. I have to break it into those 2 integrals. And those 2 integrals are exactly equal in value to each other. So I can further simplify my life is equal to 2 a mod squared integral from 0 to infinity of e to the minus 2 lambda x dx. Well, now that I have that, I need to do what Chad was starting to work on. To take the integral of e to the minus 2 lambda x dx, I just need to take my e to the minus 2 lambda x and divide by the derivative of the exponent. So I'm going to divide by minus 2 lambda. I've run out of space on this, so I'm going to go to the next page. So now I just have to put in the limits. What is the limit if x is infinity? E to the minus infinity, 0. And what is it when x is 0? Notice I factored out the minus 2 lambda, so we don't have to worry about that. What's e to the 0? So I've got a minus sign for my bracket here. That will cancel with the minus sign. Let me change color instead of canceling in black. So those minus signs will cancel, and my 2's will cancel. And so I'm left with a mod squared over lambda equals 1. Therefore, a mod squared equals lambda. What is a equal to if a mod squared equals lambda?
Square root.
This is one solution, and it's the only one we're going to use. If you wanted to include all solutions, you'd put e to the I phi, where phi is any angle. Because this will just give us something with a magnitude of 1 and some random orientation in the complex plane. There's an infinite number of solutions here, but they all have the same magnitude of square root lambda. And the e to the I phi is covering any complex value with a magnitude of 1. So I'm going to erase this because we're not going to use it. It's just possible. So when you normalize, you get your normalization constant to within a random complex value of magnitude 1, right? This can be multiplied by, it could be, for instance, multiplied by I, or multiplied by 1 plus I divided by the square root of 2, or, lots of things that could go there.
So to normalize, what are the steps?
So the normalization, the actual steps are easy to say. The work was not so easy.
Right.
The actual steps are you just set 1 equals the integral over all space of psi star psi x. If only math was as easy as the words used to describe it. And obviously, you can see from the work we did. So now we have our normalization constant. I can come back here and now say, I have psi of x comma t is equal to square root lambda e to the minus lambda absolute value x e to the I omega t, because I found the normalization constant now.
The A turned out to be square root lambda.
Yeah.
So the wave functions are there was going to have an A.
Yes, it's always going to be that way. You're always going to have to find the solution to the Schrodinger equation, then normalize. There will be other steps along the way, but you're always going to have that step. Right? We're kind of doing real quantum mechanics here. The next step, determine the expectation values for x and x squared. We brought the integral table. I didn't bring an integral table either. I can't do these we can do integration by parts, but I don't want to.
What can we include in our integral table? Like how?
You mean on tests?
Yeah.
I will bring you what you need for integral tables.
Okay. Can you provide one on Moodle that we can use for print out for our use in class?
Yeah, I should be able to.
Because I could just look for one online, but I don't know if there are some integrals on there.
Yeah.
that you don't want us to have.
I will look for what you need in that regard. Yeah, because after you've learned calculus, the fact is we expect you to use integral tables. We don't expect you to memorize all of these arcane integrals.
Right.
And yeah, you can use integration by parts. You can solve these integrals just using integration by parts. But I say just. It's a lot of pain. Who wants to go through pain? If you wanted to, don't raise your hand. So if I want to find the expectation value for x, what do I write down mathematically to find that expectation value?
Is the formula the expectation equation? Is that what
Yeah.
X absolute value of psi function of x times absolute value squared dx.
Okay, now what I wrote is a little different. What you wrote is a valid statement, but this here is the way that you need to get used to doing it. You have psi star x operator psi dx. The reason for that is the x operator action on psi will give you x times psi, and then it can be rearranged to the way you said it. But you have to do it this way. You have to, oh, I'm over time. Thank you for looking at the clock. We'll stop here.
Hotter